in the previous lecture, what we had seen was given a second order system in the closed loop, we saw how the roots moved as the gain increased, or the gain was increased from 0 to infinity. And we saw some strange behavior, that the roots were moving towards each other, they meet and then they go towards infinity and so on. So, all this was, the motivation for this was to try and understand the concepts which we were not very clear in the Routh stability criterion with respect to relative stability, right. So, we will today formalize those ideas into a set of rules and see, for given a general system, how would the poles and zeros move, especially the poles move, as the system gain is varied from 0 to infinity. Okay. And this is called the root locus plots. Okay. So, how does it go? So, let us consider a typical closed loop system, where I have the reference signal, a certain output, a gain k, g and a h, g in the forward loop, h in the feedback loop, plus and minus and so on. And I know that for this set of system, the overall transfer function is simply k times g 1 over k g h, and we now know how to derive this, right. Okay. So, this is set again just a ratio of some polynomial p s in the numerator and q s in the denominator. And we will see how the gain varies how the system behaves as the gain k is varied from 0 to infinity. We could also do for k being negative, right. So, no minus infinity, but that is a little straightforward extension once we know how it behaves when k goes from 0 to infinity. Okay. So, where do we begin with? Well, the characteristic equation which we had defined last time is simply the denominator going to 0, right. The q of s is 1 plus k times g is 0. Okay. So, I just do some manipulations, k times g, the 1 goes here, I call k times g as some p of s, and it is minus 1. Right. And what is s? The argument of p is a complex number, right, sigma plus j omega, right, when we draw things in the complex plane. So, s is sigma plus j omega, p of s is also then a complex number. Okay. Since s is a complex variable, p of s, so this minus 1 can also be then written as a complex number, right. So, so this guy, so I can split this complex number into its magnitude, its phase, and correspondingly this guy can also be split into its own magnitude and phase, and we will see what this exactly looks like, right, in terms of the magnitude of p s and the angle of p s. Okay. So, what does it mean, right. So, this from here to here, that the magnitude of this number minus 1 plus j 0 should be the magnitude of p. This magnitude is simply 1, okay. And then the angle should be the angle of this. So, what is this angle? So, this angle is 180 degree, or in a way odd multiples of 180 degree, plus minus 180 degrees, right. So, what does this mean, right. So, again I am looking for the roots of the characteristic equation as k varies, okay. So, how do I test if a particular point S naught is a solution to this equation? I am just finding solutions to this equation, right. So, this could be seen just by satisfying the angle criterion and the magnitude criterion, right, and more we will slowly build up set of rules based on just these two things, right. And slowly you will realize that what we do in the rest of the course, or most of the course, which is pending from now on, is just analyze complex numbers, nothing much. Okay. So, a system with the loop transfer function of the form k times g times h is again can be written as k, a set of zeros, set of poles, n being greater than or equal to m. So, this guy was what we called as p in the previous slide, right. So, k times g times h was p, and we need to find existence of a point or conditions of when does a point lie on the root locus. Well, the answer is whenever it satisfies these two conditions. This we will call this as the magnitude criterion, and this the second condition as the angle criterion. Okay. So, how does this look like? So, if I just take this guy here and try to compute its magnitude, this will be k times the magnitude of g times h will be k, and then okay, k is a positive number, so I do not really draw the magnitude sign here, and then the magnitude of all the zeros divided by magnitude of all the poles, right. And this should be such that the overall magnitude is 1. So, k with the product of all the magnitude of all zeros divided by the product of the magnitude of all the poles, s plus pi, this guy should be equal to 1, right. And similarly with the angle. So, this is a complex number or a phasor, as you could even call it. So, the contribution of angle of a constant is 0. There will be some angle contributions. So, these are in the numerator. So, this will be summation of all the angles of the zeros. We will slowly see how to compute this, minus, since these guys are in the denominator, minus summation of all angles of these poles. And what should this satisfy to be on the root locus? This should satisfy this angle criterion. So, summation of all angles of zeros minus summation of all angles of poles should be plus minus 2q plus 180 degrees, right, or like odd multiples of 180 degrees, right. So, these are the two conditions which we will verify. So, does the point lie on the root locus? The answer is yes, if it satisfies these two conditions. So, what was the root locus? Just to recall what we had done last time. So, we had started with an open loop pole at 0 and at minus a, and what we saw that as the gain increased, these two guys meet at some point, that is minus a over 2, and then they just go to infinity. So, this movement of poles as the gain k increases from 0 to infinity is the root locus, and you can see, and we will see slowly of what this plot means in terms of this and this criterion. Okay. So, what is the criterion? Every point S in the complex plane that satisfies this equation lies on the root locus of the system with the loop transfer function given this, right. So, this I am just looking at the open loop transfer function, right. So, how does then the magnitude criterion simply becomes, so from here k is, so this guy will go to the numerator, product of all the magnitude of all the poles and then the zeros, right. So, it should satisfy something like this, k should be such that these two things these two things should be satisfied for my any root to lie on the root locus. Okay. So, let us see what this means, right, in terms of an example. So, I have k s plus 2 over s plus 1. Okay. So, give me, so okay, let me just draw something, right. Okay. So, I just mark my poles at 0 and minus 1 and there is a 0. So, now I say give me any arbitrary point here, right, this guy. Now, I see if the gain increases, will this, so as the gain keeps on increasing, will this point lie on the root locus? The root locus could be any kind of curves on this complex plane, right. They could also go to the unstable region, but we will see that a little later. Okay. So, for any point S0 to be on the root locus, it should satisfy the angle criterion, right. So, I will have well, this guy and this guy, and I just measure the angles this way. Okay. So, this is how I measure. So, this is the angle of, so this is 0 at 2 at minus 2, this is a pole at minus 1, pole at 0, and 0 is in the numerator. So, the angle of this guy minus the angle of S of this guy minus the angle of this guy, all this should be should satisfy this equality. Similarly, k should satisfy this guy, right. So, this one, the magnitude criterion. So, summation of of this magnitude S0 plus 1 and S0 plus 2, right. So, this is what this picture says. So, if I just were to draw it, so this A would be the distance of this pole from my desired or the point which I am testing if it is on the root locus. This is A, similarly for 1 it is B and C. So, this guy. So, this if this numbers satisfy this equality, then the point is on the root locus together with satisfying these conditions, right. So, I will so then these are the corresponding angles. Okay. So, the first rule, right. So, whenever we draw a root locus, well, what are we interested in? So, let us just recall the earlier example we did, right. So, I had at 0 a pole at minus a, and the root locus is, so this guy moves this side and then they go to infinity. Okay. The first thing is the root locus is symmetrical about the real axis, and the number of branches is equal to the order of the characteristic polynomial or the number of poles of the open loop transfer function or the number of poles of g times h. Okay. So, what does it mean? So, first if I so these are this the root locus is such that it will always give me the location of the poles for different values of gain k. So, if there is a pole here, there is always a pole here because all the roots exist in complex conjugate pairs, right. So, you take any equation or any polynomial s power 6, s power 8, you see that all complex poles end up or they are they come across as complex conjugate pairs. There will just be no pole here, right. Okay. And therefore, we can say that if there is a pole here, there will already be a pole here. If there is a pole here, well, it does not matter. If there is a pole here, there will be a pole here, and so on. So, therefore, the root locus, so these roots could be either they are real, there could be imaginary or complex conjugate, right. But then if I just look at this thing, if there is a pole here, 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 and so on, and therefore, I can say that, well, whatever happens, it will always be symmetric along the real axis, right. So, the first thing is that the root locus is symmetric about the real axis, or in other words, if I just take the positive half here and I put a mirror here, this guy will just be the mirror image of this guy, right. And okay, how many branches will the root locus have? The root locus will have number of branches that is equal to the number of poles, right. So, here I have two branches, right. One branch comes from here and goes here, another branch comes from here and goes here. Okay. Now, what decides that why is this guy going here, why do not they do here and then come back to their own position, or why do not they do this and then go this way, why only perpendicular, why not this way, or why not just keep circling, all these things which we will see shortly. Okay. The second rule says that all branches of the root locus, they start at the open loop poles when k is 0 and end at either open loop zeros or infinity as k goes to infinity. So, like what we saw last time, right, we had a transfer function of the form k as s plus a, and we had two poles here, a pole at 0 and a pole at minus a, and these two guys, well, they started moving, one guy to the right, other to the left, they meet and then they diverge, right. Okay. So, the number of branches, so see that two branches meet and then they go to infinity. Now, why do these two go to infinity? Well, the rule says that the number of branches terminating at infinity is equal to the difference between the number of poles and the number of zeros of g times h. So, here there are two poles and no zeros. So, both of them will disappear to infinity. Okay. Now, how to generalize this, right. So, our characteristic equation is of this form 1 plus k g times h written as the product of zeros and poles. It looks like this. Okay. So, what am I looking at now? I am looking at what happens when, or what are the solutions when k equal to 0. Solutions means values of s. Okay. So, I take this equation, I substitute k equal to 0. So, this term goes away. So, I am left with this guy, right. So, what are the solutions, what are the values of s here such that this expression goes to 0? Well, these are precisely the poles of the open loop system. Okay. Thus, for all the open loop poles are a part of the root locus, and the root locus exactly starts from those poles, and these are again the open loop poles. Okay. Now, where do they go? What about the zeros? Okay, I can rewrite this equation I just get divide by k and I get something like this, right. Now, the equation can be rewritten in this form. Now, what am I looking at? I start from k equal to 0 and I ask another question. Now, what are solutions or again values of S when k goes to infinity? Okay. When k goes to infinity, I know that this guy disappears. Okay. If this guy disappears, what I am looking at is an expression which is like this. Right. Now, what are the solutions to these guys? Right. The solutions of these guys are the open loop zeros, right. So, at k equal to 0, we start at the poles and k equal to infinity, we end, that is the final point which we look at, we end at zeros. Okay. So, what I can say that also the zeros lie on the root locus and these are the terminating points. So, I poles at k equal to 0, I start from the pole and I end at 0. Okay. But what we know is that the number of poles is usually greater than the number of zeros, right. Or it could also be equal. So, but these are m, number of poles are n. So, what I could say is that only m poles terminate at zeros, right. Okay. What happens to the remaining n minus m poles, right. So, if I say well this remaining n minus m poles, they go to infinity. So, let us see okay, what this could mean. Again I am looking at solutions of the characteristic equation which is 1 plus k the product s plus z I over the product is over m, here it is over n, s plus p I equal to 0. Okay. So, let us do a little example and I say well I take an example like okay. So, let us say sorry. Okay, say g times h to 0 and I want to see okay what how does this look like. This is s plus 2, s plus 3, 1 over k, s plus 1 is 0. Okay. So, I want to see, so this is exactly what we had, right, 1 over k the product of the poles and zeros, this guy should go equal to 0. Okay. So, for sure one solution is s equal to minus 1 as k goes to infinity, because this guy disappears and I am just looking at this solution. Okay. Now, are there any other solutions to this equation? Okay. So, let us rewrite it in a slightly different way. So, I have 1 over k is s plus 1, if I just write the magnitude part, s plus 2, s plus 3, and I am interested again in what happens as k is going to infinity. One solution again as k goes to infinity, this guy goes to 0, so s equal to minus 1. So, what we could always or what we can always or also observe is that well something similar happens even when s, which is okay the magnitude goes to infinity and maybe some whatever angle here, right. Another solution could be just you can just substitute it here, to take the limit and you see that as s goes to infinity this guy goes to 0, right. So, you can just do 1 over divide by s square and then check all the stuff, right. So, another solution is s going to infinity, right. Okay. What happens then at s equal to infinity? The value of the transfer function or the open loop transfer function g of s, h of s, when is s is is infinity, of course with k also being infinity, this guy goes to 0. Okay. Now, these are what I call as zeros at infinity, right, because even at this value at infinity the value of the transfer function goes to 0, right, because that is the definition, right, g at some 0 is 0, right. Now, take this example, right. So, if I just take the other day we were doing the example of 1 over s plus a, right. Similar thing holds here, and both the roots are actually now going to what we call as again zeros at infinity. Okay. So, the thing is the first, so here there are 2 poles and 1 0, one pole will end up at a 0 which is -1 and the other pole will go to the 0 at infinity. Okay. Now, the third rule will say that okay, take a point on the real line, say for example this point right here, sorry, say this point. Now, say does this point lie on the root locus? Well, let us see if we could try and find an answer to that. A point on the real axis lies on the root locus if the sum of the poles and zeros on the real axis to the right is an odd number, right. So, this sum is actually just the number of poles plus number of zeros, it is not the values of the poles, right. It is just say for example, if I am looking here from here to the right, I just say well there are 2 poles and 1 0, 3 poles and 1 0, 4 poles and 1 0, 4 poles and 2 zeros and so on, and I take the total numbers, like I have here I have 3 poles and zeros, 4 poles and zeros and so on, right. So, we look at the number of poles and zeros, not the values of it. Okay. So, why is this true? Okay. So, again the root locus should satisfy the angle criterion. So, let me take a point here and I call this point as S naught. Okay. Now, what is the angle? Okay, sorry, this already S naught is mentioned here anyways. Okay. So, this is S naught, right. So, what happens at S naught if I measure the angle? Well, from this pole contributes an angle 180 degrees, this pole contributes an angle 180 degrees, this pole contributes an angle of 180 degrees. So, this is a 0, so it will contribute an angle of plus 180, right. So, all these angles will, this will be the contribution. What about these guys? If I just measure the angle from the right, so they will just be 0 degrees, right, they do not contribute to the angle. So, 180, 180, 180. So, we will see if this point satisfies the angle criterion or not. Okay. So, why do not we, what about complex conjugate poles? Well, the sum of the angles is always 0. So, as we can see from here, right. So, this angle here plus this angle will always go to 0 or 360 degrees whatever. Okay. The angle contribution by every poles and zeros on the real axis to the right of the test point is 180 degrees, these are to the right, to the right, to the right, it is 180 degrees, and then to the left of the test point is always 0, these guys do not contribute, P3, Z2, P4, they do not contribute. Similarly with and then you can see the complex conjugate guys here, the overall angle goes to 0. Okay. So, what is the total angle contribution? Right? The total angle contribution is the angle of all the poles and the angle of all the zeros. Well, so here P1 contributes 180, P2 180, Z1 180. If I use the appropriate signs, 1 minus 180 for the poles at P1, minus 180 for the pole at P2, and all these guys are 0. The first 0 here contributes an angle of 180 with the plus sign, and this is 1. Right. And this guy is an odd multiple of 180 degrees, and therefore, S0 is a point on the root locus, right. So, therefore, this justifies our thing saying that the point on the real axis lies on the root locus if the total number of poles and zeros to the right of that point is an odd number. Okay. Similarly, I could even do for some other point, say S1, which is now. So, earlier S0 was between P3 and Z1. Now I take this point, right, and I call it S1, and I just check is S1 on the root locus, right, and I just look at the angle criterion again. So again I have P1 contributing an angle 180 in the negative direction, the pole P2 again minus 180, I have a 0 that contributes plus 180, P3 contributes minus 180, contribution of P4 and Z2 will be 0, and the complex conjugate guys will anyways be 0. Okay. So, let us do this minus 180, minus 180, minus 180 plus 180, and this is 360 degrees, right, and 360 degrees it does not satisfy this criteria that it should be an odd multiple, right. So, 360 is an even multiple. So, if you look at the angle criterion, what was the angle criterion? It should be plus minus 2q plus 1 times 180 degrees. This should be the angle of g times h. Okay. So, this is an even multiple, therefore, S1 is not a point on the root locus. Okay. So, let us end with an example. So, if I take a system with poles at, so poles at minus 2, minus 4, a pole at the origin and these two zeros. Right. So, what is the first observation is that the number of poles is 3, right, and therefore, the root locus will have 3 branches. Okay. Now, where will these branches go? That depend on what are the locations of the zeros, right. So, take these two zeros and say, well, there are 2 zeros, sorry, and 2 poles, oh sorry, 2 zeros and 3 poles. So, 2 of those 3 poles will go to the zeros and one remaining one will go to infinity, right. Okay. So, let us quickly draw the pole 0 diagram. So, I have a pole at 0, I have a pole at minus 2, I have a pole at minus 4. Okay. So, let me just take for example, say does this point lie on the root locus? I see, well, there is only one pole to the right. So, of course, this is on the root locus, this is also on the root locus, this entire thing will be on the root locus, right. So, this pole will start here and then move towards this 0, and we know that, well, the poles terminate at 0. So, this is when k equal to 0, this happens when k equal to infinity. Now, look at what happens to this guy. Does this guy move towards the right or towards the left? We will again see the same the condition number 3. Okay. Now, is this point on the root locus? Well, the number of poles plus zeros is 2, it is an even number, even is not allowed. So, this entire region here is not on the root locus. Okay. So, therefore, this guy will, okay, now let us check this region. Is this region on the root locus? Okay, look to the right, there is 1, 2 and 3, the total number of poles and zeros is an odd number, and therefore, this entire region is on the root locus. Okay. So, this guy will slowly move this side and then terminate at 0, again k equal to 0 till k equal to infinity. Okay. Okay. Now, what about this guy? Can this guy move towards the right? Well, just see what happens in this region. I have 1, 2, 3 and 4 poles, which is 4 poles, 1, 2, 3 and 4 are the number of total number of poles and zeros, which is an even number, and that is not allowed. So, this entire region is also out of picture. Now, go here, right, to the left. Is this, does this satisfy the condition number 3? Okay, say 1, 2, 3, 4, 5 are the total number of poles and zeros. Of course, so this is on the root locus, this is on the root locus, and this entire this real axis to the left is on the root locus, right. Okay. So, what does the second condition say? That when k equal to 0, I start at the poles and end up at 0 when k equal to infinity. Similar things happens here. There are, in this case, there are 3 poles and 2 zeros. So, 2 poles go to 0, and by the rule 2, 1 pole goes to infinity or the 0 at infinity, and you see this entire real line from here from to the left of minus 4 till infinity is on the root locus. So, this is the third guy that will, which will go to infinity, right, and this entire this will tell me the entire behavior of the system as the gain k is varied from 0 and 0 to infinity. So, these were the first 3 rules in construction. So, in the next lecture we will see some other rules related to these things. Okay, thank you.